And in this video I am going to discuss with you how to obtain electric field electric field of a uniformly charged thin rod at a point which is lying on its perpendicular bisector. Hello students, myself Sumit, physics faculty, and in this video I am going to discuss with you how to obtain electric field of a uniformly charged thin rod at a point which is lying on its perpendicular bisector. Okay, at a point which is lying on its perpendicular bisector. So let me consider this rod. Okay, and this rod is having a length L. Okay, having a length L. This is an axis which is a bisector. Okay, perpendicular to it, passing through its midpoint, and let me take this midpoint as origin. Okay, so this extreme left end of this rod, it is having a position x equal to minus L by 2, and this extreme right end, that is having a position x equal to plus L by 2. Okay, there is a charge, a positive charge is spread on it, and linear charge density, linear charge density is lambda Coulomb per meter. Okay, that is, this much is the linear charge density, that is charge per unit length. Okay, charge per unit length for this rod, that is lambda. Okay, now I want to find out, I'm taking a point P here on this perpendicular bisector, and I want to find out electric field here. So for that, what I will do, I will first consider a charge element at a distance x. Okay, I'm considering this x is a variable. Okay, I'm considering that there is a charge element there from a charge element there which is at a distance x from the origin, that is midpoint of this rod, right? So what will be the electric field? What will be the electric field due to this charge element? Okay, that will be in this direction, right? If I make a line joining this charge element with the point, then let me make another one. Okay, then this line, if you are joining this point with this charge element, okay, then that electric field due to this element, and I say it is dE. Okay, so this dE, electric field due to this charge element, and how much charge this element is having? That is having charge, so you can write elemental charge dq is equal to lambda, that is linear charge density, into its width. Okay, and I am considering that this charge element is dx length long, right, along the x-axis, and dx length long. So this elemental charge, that will be lambda dx. Okay, that will be equal to lambda dx. Now if I write what is the expression for electric field due to charge element, that will be equal to 1 over 4 pi epsilon naught dq divided by this length. This length is square. Okay, square of this length divided by square of this length, and let me take this length as r. So what is r? if I am assuming that this height from the origin, and I am assuming that this rod is a thin rod, right? So let me take this height as y. Okay, that this point is at height y from the origin, that is midpoint of the rod, right? So I can write from here that this is small r, that is distance between this charge element and this point, that will be equal to square root of x square plus y square. Okay, that will be equal to square root of x square plus y square. Now suppose I take another charge element, and that is also at a distance x from the origin. Okay, at a distance x from the origin. Okay, then what will happen, that electric field due to this second charge element, that will be in this direction, right? That will be in this direction. Okay, this is electric field due to the first charge element, this is electric field due to the second charge element. Okay, and they both the electric fields, they are making an angle theta with the horizontal. Okay, theta with the horizontal. Okay, so what will happen, that x component of electric field due to the first charge element, that will cancel out the x component of electric field due to second charge element. Okay, so from here we can conclude that no matter where I am assuming my charge element, okay, on this right side, at whatever position I am assuming my charge element, there will exist a charge element on the opposite side, such that it will cancel out the horizontal component due to the first one. Okay, so we can say that this net electric field, that will only be along the y-axis. Okay, I am assuming this y-axis. Okay. Okay, so this is your y-axis. So your electric field, that will be along the y-axis. Only that component is surviving, and this is your x component. This is your x-axis, right? And let me write some clearly. So this is your y, okay, and this is your electric field due to the second charge element. So net electric field due to this thin rod, uniformly charged thin rod, that is along the y-axis, that is along the perpendicular bisector itself. Okay, so let me write what is dEy, that is x component of the electric field due to charge element. Okay, so that will be equal to dEy, that is y component of this electric field, that will be equal to 1 over 4 pi epsilon naught dq by r square sin theta. Theta is this angle. Okay, theta is this angle. Okay, so if theta is this angle, then from here, from this right angle triangle, I can see that this sin theta, that is equal to what? That is equal to y divided by r, that is perpendicular divided by the hypotenuse. Okay, so I can write that this dEy, that will be equal to 1 over 4 pi epsilon naught dq by r square. Sin theta is what? Sin theta is y over r. Okay, so that is y divided by r. So this dEy, that will be equal to 1 over 4 pi epsilon naught, okay, y dq by r cube. Okay, now what is dq? That dq is lambda dx and r is square root of x square plus y square. So from here I can write that this dEy, that will be equal to 1 over 4 pi epsilon naught y lambda dx divided by x square plus y square raised to the power 3 by 2. Okay, that will be the electric field, in y direction due to that small charge element. Okay, now if I want to find out what will be the total electric field in y direction due to the uniformly charged rod, that will be equal to 1 over 4 pi epsilon naught. Okay, that is a constant. Y is also a constant, so I can take it also outside, and lambda is also a constant, so I can write that this lambda y divided by 4 pi epsilon naught dx divided by x square plus y square raised to the power 3 by 2. Now what are the limits of x? Okay, what are the limits for this integral? Okay, those limits are from minus L by 2 to plus L by 2. Okay, okay, you can also write here. Okay, so this Ey, that will be equal to what? That will be equal to lambda y divided by 4 pi epsilon naught, then minus L by 2 to plus L by 2 dx divided by x square plus y square raised to the power 3 by 2. Okay, now I can also write it as 2 lambda y divided by 4 pi epsilon naught 0 to L by 2 dx divided by x square plus y square raised to the power 3 by 2. Okay, how I have written this? We know that there is a property of integral, of definite integral, that suppose this is your definite integral, limits are going from minus a to plus a, fx dx, then if fx is an even function, if f minus x, if f of minus x is equal to fx, that means if f is an even function, then I can write that this will be equal to twice of 0 to a, that is an integral which is having limit 0 to a. Okay, fx dx. And if f minus x is equal to minus fx, then this integral will become 0. So okay, so using that property I can write this, or I can write this lambda y divided by 2 pi epsilon naught. Now our task is to solve this integral, right? To solve this integral, so I can write this 0 to L by 2 dx x square plus y square raised to the power 3 by 2. Okay, forget for some time limits here. I want to first solve this indefinite integral. Okay, so let me take, so I will do that using substitution method. So I can write, because x is a variable here, so I can take a new variable in place of x. I can write that x is equal to y tan alpha, that I am assuming, okay, in terms of a new variable alpha. So I can write this dx as what? I can write it as y sec square alpha d alpha. Okay, I can write this dx as y sec square alpha d alpha. And what is now x square plus y square will give me? That will give me y square tan square alpha plus y square. That means that will be equal to y square sec square alpha. Okay, so this integral, that will become what? That will become in place of dx I will put y sec square alpha d alpha, and this denominator, that will become y cube sec cube alpha. Okay, now that that will become 1 over y square, as y is a constant, so I can take it outside. Okay, 1 over y square, and this will become cos alpha d alpha. Now what is cos alpha? Integration of cos alpha, that will be equal to sin alpha. That will be equal to sin alpha. Okay. Now we know that x is equal to y tan alpha. So I can draw an imaginary right angle triangle which is having, so I can write from here that this tan alpha is equal to what? That is x over y. Okay, so there is a right angle triangle, an imaginary right angle triangle I can take, which is having a perpendicular as x, base as y, so its hypotenuse will be x square root of x square plus y square, right? That will be its hypotenuse. Okay, so I can write this integral as 1 over y square, and from this imaginary triangle I can write that sin alpha is what? That sin alpha is x divided by square root of x square plus y square, right? So that will become x divided by square root of x square plus y square. So that will be this integral, right? That will be this integral. If I take limits from 0 to L by 2, then what will happen? Okay. I take limits from 0 to L by 2. Okay. So let me write this. Okay. What we have solved? We have solved this integral, right? This one. Okay. So dx divided by x square plus y square raised to the power 3 by 2, limits are varying from 0 to L by 2. So I can write here limits are varying from 0 to L by 2. So it will become what? Let me go in previous slide. Okay. Yeah, it's okay. Okay. So you can write now L by 2 divided by square root of L square by 4 plus y square minus 0. Okay. It can also be written as 1 over y square. This is L by 2, and this will become in denominator L square plus 4y square. If a 4 is taken common from here, okay, 1 by 4 is taken common from here. So I will left there will also be 1 by 2 here. Okay, that is L by 2 divided by in denominator square root of L square plus 4y square divided by 2. Now this 2 will cancelled out by this 2. Okay, so what it will give me? That it will become 1 over y square. Okay, then L divided by square root of L square plus 4y square. If I put this expression, that is this integration. Okay, that is this integration. Okay, 0 to L by 2 dx divided by x square plus y square raised to the power 3 by 2. And if I put this integral into this expression, so I will get what is the total electric field. Okay, so that will be equal to what? Just you multiply it by that Ey is what? That Ey is lambda y divided by 2 pi epsilon naught into this integral, right? And what is the value of this integral? That is 1 over y square L divided by square root of L square plus 4y square. Okay, one power is cancelled out in denominator, so I will left with Ey equal to lambda divided by 2 pi epsilon naught. Okay, 2 pi epsilon naught y, and in bracket this quantity L divided by L divided by square root of L square plus 4y square. Okay, now this is the total electric field, right? This is the total electric field at that point on the perpendicular bisector, due to this assumed uniformly charged thin rod. Okay, this much will be the electric field. Now take me one special case. Okay, one special case. So we have calculated electric field due to a uniformly charged thin rod at a point on its perpendicular bisector. This rod is having a length L and linear charge density lambda. Okay, and what that expression comes out to be, that is lambda divided by 2 pi epsilon naught y into L divided by square root of L square plus 4y square. Now let me discuss with you a case here. Okay, that if y is much greater than L. Okay, if y is much greater than L, this height is y. Okay, it is situated at a height y from this rod. Okay, this is y, this height is y. Okay, so what happens when y is much greater than L? Then in that case Ey, that will be equal to lambda over 2 pi epsilon naught y. Okay, I can take 4y square common from here. So I will left with in square root there will be L square divided by 4y square plus 1. From here I can see that if y is much greater than L, then L over y, that is much less than 1. Okay, so this quantity L square by 4y square, that is very much less than 1, so I can neglect this. And as I am taking 4y square common from this square root, so I will get a term 1 over 2y. Okay, so this will give me what? This will give me Ey equal to lambda L divided by 4 pi epsilon naught y square, and I can write this lambda L as Q, that is total charge that is uniformly distributed over this rod. Okay, if I multiply this lambda by the length of the rod, then that will be the total charge spread on this rod. Okay, on this rod. Okay, then Ey will be equal to Q divided by 4 pi epsilon naught y square. So what does that mean? It means that 4 points which are very much far away from the rod behaves like a point charge. Now let me discuss with you another case. What happens? Another case, if rod is having infinite length, then what will happen? So what happens in this case, that this L that is tending to infinity. Okay, so from previous slide I can write this expression for Ey. Okay, so this Ey is actually equal to lambda divided by 2 pi epsilon naught y into L divided by square root of L square plus 4y square. Okay, if I take L square common from here, then what will happen? I take L square common from that square root, so I will get 2 lambda divided by 2 pi epsilon naught y this is your L, okay, and one L you are that will come outside of this square root, and you will left with 1 plus 4y square by L square, right? Now as this L is tending to infinity, okay, this L will cut this F, okay, this L is cancelled out by this L, okay, in the denominator. So when this L is tending to infinity, this term that will become 0, okay. So I will left with lambda divided by 2 epsilon naught y into 1, okay, that is 1 now. So this much will be the electric field, due to a uniformly charged thin rod of infinite length. Okay, we can also find that electric field due to uniformly charged thin rod of infinite length. If that rod is having infinite length, then we can also find this expression using Gauss law. Okay, using Gauss law. Okay, thank you.